Welcome everybody to BATNAV's webinar in our supplier series. Today we're talking to Economical Energy from South Australia. They've been around since 2019 and they're looking at a different way to do energy storage and looking at what most energy storage is today, as in gravity energy storage. Today, the majority of energy storage that we have at the utility scale is pumped hydro energy storage. In the USA alone, there's 43 pumped hydro plants, 22 gigawatts of capacity and 553 gigawatt hours of energy capacity. Our guest today is Matthew Forrest from Economical Energy, who looked at some of those facts a few years ago and realized that there might be a different way to deliver energy storage, and has taken the bold and brave move to start his own startup in energy storage. Matt, thanks for joining us.
Thanks for having me on, Dave. Appreciate it.
So Matt, tell us about how you came up with your ideas for Economical Energy.
Yeah, so being based in South Australia, actually first started thinking about energy storage when we had some really bad blackouts back in 2016. And at that point, I was most of the way through my engineering degree. And there was a lot of talk in the media about, what was the cause of the blackouts? Was it renewables, the intermittency, that sort of thing? Or was it the transmission lines that got blown over? But that's when I really first started thinking about storage and how it worked with renewables.
Yeah, right. And so you were at university at that time. Was there a lot of discussion around that with the other students or professors, or is this something that you just dug into yourself?
This was just something I dug into myself, sort of out of my own curiosity. Did a bunch more research and kind of added on to the knowledge that comes from an engineering degree.
So you're digging into what energy storage was and how you could actually do it. And so then what did you do?
Well, I guess it really started with a first principles approach. So I started with considering the different known methods that there are for storing energy, as well as the different trade-offs that there are with them. So the sort of first ones that came to mind were electrochemical, what we see with most battery chemistries today, thermal energy storage, storing energy and heat, hydrogen, that's very big in the media, and then also gravity, which, like you mentioned, already accounts for most energy storage. And so working through those different mechanisms, different properties, different features, different levels of scalability. And what really became apparent from this is that gravity was just a really great place to start. Already been accounting for so much, so it showed that it had scalability. And another really valuable feature is that there's no fundamental energy losses associated with the physics. And so high round trip efficiencies are achievable.
Okay, great. So you looked at the different potentials for storing energy, and gravity was the one that you thought made the most sense.
Yeah, it looked like it was the most likely to be able to be sort of reinvented or reconsidered, redesigned.
Yeah, it's interesting to say most likely. So there was a certain amount of uncertainty in your mind that energy storage was going to be able to do the job that it needed to do.
I think what was apparent with the big battery that Tesla built in South Australia was that it was very expensive, and in the scheme of grid scale storage was very small. And so it really was apparent that we need a lot more and we need it a lot cheaper.
Yeah, okay. So you were looking at gravity-based storage. That's where you thought there was the best chance of actually scaling it out to what the human civilization needs to be able to execute the energy transition. And then you looked more in depth at pumped hydro.
Yeah, that's right. And so some of the things that are pretty apparent about pumped hydro is that it needs specific topology. So you need mountains, and not only do you need mountains, you need mountains that are close by to each other. Has a lot of land use. Typically when you need to build big reservoirs, they're often kind of flat, and that means flooding large areas. There's often quite severe ecological impacts. So by damming rivers, or even just flooding areas that would otherwise be ecologically diverse, or even spreading pest fish species between bodies of water. It's also often quite distant from transmission infrastructure, and that adds to the system cost in actually connecting it to the electricity grid. And it's also impacted by rainfall. Both too much and too little can impact whether there's water available to go down the hill, or whether there's enough room for the water down the hill.
Yeah.
And particularly in a country like Australia, where we often have droughts that add challenges. Sort of coupling energy security with water security didn't sound like a great idea.
Yeah, the challenges, particularly in a large country like Australia, is that the distance and the rainfall and the topology definitely make it challenging. All right, so then what did you do?
So I started thinking about alternatives to pumped hydro. And so that started with thinking about the equation that really describes how gravity energy storage works.
Mm-hmm.
So energy is mass times height times gravity. And so if you're trying to engineer a system to store the most amount of energy for the cheapest capital cost, then you'd need an awful lot of mass and an awful lot of height. And height is something that pumped hydro often struggles with. But think about the height component. The tallest building in the world is roughly 800 meters tall. The deepest mine in the world, 4 kilometers deep. So in terms of getting access to vertical elevation, going underground seemed like a great place to explore. And additionally, I guess you can store large quantities of mass in piles on the ground and sort of use the rock or surface of the earth as the structural thing, as opposed to building upwards.
You kind of told everybody what your ideas are. You looked at the mass, you got to have something very dense. And then height, well, going up is hard, going down probably a lot easier. And height, for example, yeah. Matt, you're going down underground. That's your concept. Tell us about how the system will work.
Yeah, so probably the shortest way that we can describe it for people who know what pumped hydro is we can describe it as pumped hydro but with pellets. So instead of using water, we use a granulated mine waste and transport that between a surface stockpile and a deep underground stockpile. And the nature of it being deep underground means we can really leverage that height component. Mm-hmm.
Okay. So it looks like a big operation. You've got several piles there. You've got shafts going down, stack of reclaimers under the ground. You've got a access tunnel and the generators there as well. It's a lot of gear.
There is a lot of gear, but it is interestingly all equipment that's largely used in the mining industry already, equipment and processes in construction and operation.
Yep. So I was thinking about this as I was looking at this diagram before and going, well, you're just moving a lot of material around. That seems pretty inefficient to me. But then when I thought about it, we move heaps and heaps of coal around for coal-fired power plants all the time. I spoke to a friend recently who works for a port company, and they have, just to export their coal, they have the biggest bulldozer fleet in Australia, which you can think we have some pretty big mines and they would have large bulldozer fleets. So there's a lot of just movement of materials that we do in the economy today. So this is not really any different. And you're saying that all this equipment is already proven and used in the mining and minerals processing industries anyway.
For the most part, yeah, with the exception of our vertical bucket elevator.
Okay.
That's got some additional, I guess, specifications so that we can get the sort of power capacity that we need out of small diameter shafts. The shafts that we're looking to drill are only in the order of 1 meter diameter.
Okay.
You'll get quite high mass flow rates and therefore quite high power capacity through that.
Great.
By making them smaller, that really cuts down on the capital cost and time to build.
Yeah. Excellent. And so let's take a little closer look at some of the other equipment that you've got there. What are we looking at here?
Yeah, so on the left, we've got a cross section of one of the Viper head sprockets, and sort of trailing along below that is the rest of the proprietary bidirectional bucket elevator. And that's sort of the small diameter thing that can move a lot of material through the small diameter shafts. So that's sort of the key component that facilitates what we're trying to do. And then on the right, it sort of shows more of the overall top architecture. So it's got the equipment that does the lifting and lowering on the left of the right image, and then sort of large stockpiles that can hold your tens or hundreds of kilotons of mass, with belt conveyors for moving the material on and off of that.
Yeah, it's not something I have experience with, belt conveyors, definitely. So you've got the effectively little buckets going up and down into the ground, and it's just moving that big sprocket at the top, which drives the generator.
That's right, yeah.
Okay, pretty simple. And this detail, what are we looking at here?
This is another detail of the head sprocket on the surface.
Mm-hmm.
And so it's sort of a large-ish diameter, low RPM piece of equipment, coupled to a gearbox, quite similar to what you'd find in a wind turbine. So going from a few RPM on the output side to a few thousand RPM on the generator side. That side of it's all pretty pretty standard engineering.
Okay. And these conveyors, are they used in the mining industry at the moment to lift vertically in this way?
We're actually looking to sell these conveyors into the mining industry as well.
Okay.
Because they, have a lot of advantages over existing hoisting methods.
Right.
So that's we've got some intellectual property around the manufacturing process that sort of facilitates the, I guess, structural loading that it sees in operation.
Right. So you said that there could be an innovation not just in energy storage, but materials handling as well.
Yeah.
Nice. Tell us about where your system will really excel, because energy storage is, there's different systems, different applications. Where do you think your system will win out?
Yeah, so our Viper system really only makes sense at the utility scale. So it's not going to go in your backyard or at your small or medium-sized factory.
Mm-hmm.
Our first versions of this will be installed with existing underground mines. And so that means the sort of minimum product size for that is quite a bit smaller, around 5 megawatts. And once we've sort of proven it out at this scale, we'll be able to do standalone projects that can be built nearby to existing energy transmission infrastructure or generation assets like wind or solar farms.
Yep.
And so that'll have to be a bit bigger, and that's really to offset the additional cost of building an access tunnel to deep underground.
Yep.
And that brings the minimum commercial scale up to about 150 megawatts.
Yeah, okay. So you got a commercial pilot around 5 megawatts, prove out the technology, make some improvements. I guess you're going to test a few things, and then economics wise, you're looking at 150 megawatts plus.
Yeah, for the standalone versions.
Great. What sort of megawatt hours would you think is suitable there?
So generally, with this technology, we're kind of targeting the 8 to 12 hour storage range. Okay. And that's sort of the trade-off between the sort of properties of the technology and the properties of the energy market in terms of the difference, the time difference between when there's energy surplus and energy shortfall.
Yeah.
And you think of like 12 hours intuitively, it's like that's sort of how long the sun is up for. So it makes sense intuitively that that's the primary frequency to store energy at.
Yeah, and like most energy storage systems, this one is largely modular as well. As long as you have the footprint, you could just add another system next to the existing ones if the economics actually justify it.
Yeah, that's exactly right.
Yeah,
that modular nature really means that you can build it and go, cool, now we want some more, you can add some more, and also the modularity sort of adds to I guess the process of like learning rates. When you're building the same thing over and over again, you can develop better processes for doing things easier, quicker, cheaper. Yeah,
great. And other advantages you were telling me before is around the ability to provide system strength. So we talked about this at length before we started this webinar, and you gave me a bit of an education on what it actually is all about. So maybe just take a little bit of time to explain what system strength is to someone that may not be familiar with it and why that's important.
Yeah, so system strength is a property of the transmission and distribution grids, and it really has to do with the impedance or resistance of the transmission lines, and also the generation sources. So on the slide here, we've got a chart comparing high system strength to low system strength.
Mm-hmm.
And system strength is most relevant in the event of faults or issues or problems happening on the grid.
Mm-hmm.
And so in a system with high system strength, when there's a fault, the waveform is essentially distorted less, whereas in a low system strength, it sort of gets a whole lot noisier. And that's particularly relevant to grid following inverters when they're coupled to the grid. So, most wind and solar inverters on the grid today are grid following inverters, and they're more likely to be disrupted by electrical noise in the event of faults.
Mm-hmm.
And that can actually cause them to trip offline, sort of like what happened in the SA blackout case.
Okay. And how does your system provide system strength?
So our system uses synchronous motor generators. So they're actually, it's not inverters that connect it to the grid. It's the same big spinning machines. They're connected to gas and steam turbines.
Okay.
And so that's, big rotating machinery with electromagnetic fields and sort of low impedance copper coils.
And where is system strength important in a network?
So system strength is something that AEMO speak about quite a lot in terms of operating the energy grid in a stable manner. So the plot on the right shows a map of Australia's national energy market and indicates the areas where there's high and low system strength.
Mm-hmm.
And areas where there's low system strength are actually areas where it can be challenging to connect inverter-based generation to the grid,
mm-hmm.
And where inverter-based generation can actually be curtailed for reasons of system strength. So not just like economic curtailment when the prices are low, but actually curtailment because it will destabilize the grid.
Right.
And so comparing that with the graph on the left, you can actually see that some of the areas where you'd really like to build a solar farm are actually areas where there is grid, but it's weak system strength grid.
Mm.
And so one enticing application for our technology is for it to be built co-located with solar or wind farms in those sort of areas where it can both provide the storage during the middle of the day and also provide the system strength so that you can actually make good use of the high solar irradiation areas.
Yeah, and I noticed that over there in South Australia where you're based, the system strength is not so great.
Yeah, I'm not sure whether that was before or after the synchronous condensers were installed in South Australia.
Yeah, probably improved a bit. So you think that the system strength has improved in South Australia, and that is because of these things?
Yeah, so Electranet, South Australia's transmission service provider, have recently installed 4 synchronous condensers, which are basically big spinning synchronous motors without a load attached. And so these were $166 million capital cost. And their role is really to add that system strength, and that's basically all they do.
Right.
They can do a bit in terms of reactive power supply.
Yeah.
But yeah, their primary role is to add that system strength.
Okay.
And so what a Viper system could do is sort of contract to those transmission service providers and say, hey, instead of you installing synchronous condensers,
yeah,
why don't you pay us a bit? And that'll sort of help our business case
yeah.
along for building a storage solution that adds system strength to the grid as well.
Yeah, and you get the renewable energy storage as a bonus.
Yeah, or it kind of adds to the business case for the overall project.
Matt, how long have you been working on this project?
So the idea was conceptualized back in 2019. And since then, we've been working on sort of commercial viability and sort of building a company around the technology.
So you did a pre-seed funding?
Yeah, back in 2021, we had an oversubscribed pre-seed funding round. And that sort of helped us along the way. Great.
And what are some of the other milestones you've achieved?
Yeah, so one of the really big ones was actually receiving a clear report on patentability. So that's essentially we file a patent to IP Australia, and they've then done an international type search and gone, has anyone else done this before? What things are similar? And what they've concluded is that this is sort of a novel and inventive approach, and that sort of gives us really good confidence that we'll have a patent granted for the technology once it goes to examination in the various jurisdictions around the world.
Yeah, great. And you've had some involvement with the Energy Lab?
Yeah. So we had some investment and we participated in their Climate Solutions Accelerator last year, which was excellent in terms of meeting a whole bunch of investors and very knowledgeable people in the energy industry.
Yeah, great. And what's the commendation award that you received?
Yeah, so this was at the 2021 Premiers Awards in Energy and Mining. And so that was sort of acknowledgement from the South Australian government of our work and successes.
Great. And technical paper?
Yeah, so we've put together a handful of documentation, but one of these detailed engineering reports we had reviewed by an impartial expert, Dr. Lee Chen, at the University of Adelaide's School of Mechanical Engineering. And that was just sort of to go, we've done our homework. What do you think? Is this? Have we made any mistakes? Have we made any oversights?
Yep.
And he sort of come back and said, yeah, it all looks right as far as I can tell.
Yeah. Okay. Good. That must have felt good.
It was. Yeah. It was certainly a very reassuring step.
Yeah, excellent. And as far as the company and the team, tell us a little bit more about that.
Yeah, so we've assembled a team with a broad range of experience and skill sets. And so that'll really help us bring the technology to fruition. So both at sort of the high level leadership on the board of directors, a lot of experience, and then the technical team for digging into the nitty gritty and designs and that sort of thing.
Yeah, great. It looks like you've got a team of senior people there that have worked across different sectors and you know, not just the technical side, which is really important, but you've got a group of young engineers with sort of diverse areas as well, which is a great compliment.
Yeah.
Matt, this is pretty exciting, and you've done a lot of work to get here. I know how hard it is to take something, an idea, and build it to where you've got. So it's a huge commendation for you to get to that point. What does the future look like for you?
Yeah, so we're currently working on a commercial pilot plant, and this is looking like being installed at an underground mine in South Australia. So that would give us about 250 meters of vertical elevation. And as far as the scale goes, we're thinking the order of 500 kilowatts and 10 hours of storage. And even for this small scale first pilot, we think we will have the capital cost of storage on par with lithium-ion home batteries, which we think is a very promising step. And following this, we're working on a seed funding round to finance this project.
Okay, great. And we talked about this plot before, which you have prepared from your knowledge of the South Australian energy industry, or our South Australian energy market. Tell everybody what you see here and how that relates to economical energy.
Yeah. So in summary, what this graph is showing is the increasing market for long duration energy storage. So starting with the green line, what that's showing is that the average renewable energy percentage on the grid is increasing. And what that means is that when there is a surplus of renewable energy, prices go down. That's what we typically see. When there's a shortfall, gas and diesel generators have to take over, and that pushes the price back up. And so that increases the difference between the lower prices and the higher prices, and increases the margin that energy storage can make by buying energy when prices are low and then selling it later when prices are high. And so the blue columns show the annual arbitrage profit for a 1 megawatt 8-hour storage system. And essentially, as renewable energy goes up, price variability increases, and so the amount of revenue that can be derived from operating an energy storage system to perform arbitrage is increasing in parallel with that. And that's something that we expect to continue happening as more renewable energy is added to the grid.
Yeah, great. Excellent. Well, that's exciting for you, and I wish you all the best with economical energy. Look forward to hearing about the commercial plant or the pilot plant when you get that up and running, and maybe we can come out to a site and have a look at it.
Yeah, thanks a lot, Dave. It'd be a pleasure to show you around.
Great. Thanks a lot, Matt. Bye.
Yeah.